Good day. Today we will be going to discuss about rheology. All throughout the video, we will be going to talk about what rheology is, the application and classification of rheology, and also about the stress and strain. What is rheology? It is defined as the study of the flow and deformation of matter. Rheology is particularly concerned with the viscous flow and elastic deformation of liquids and solids. Who is Eugene C. Bingham? Eugene C. Bingham was a professor in Lafayette College. He founded the Society of Rheology in USA and coined the term rheology, and its root lies in the Greek word for flow. It includes the theory underlying the deformation and the practice of measurement. Example of rheological properties. Viscosity. Viscosity is a fundamental rheological property that describes a fluid's resistance to flow, and it is a critical parameter in understanding and predicting the behavior of materials across diverse applications. Elasticity. Elasticity is one of the fundamental rheological properties that describes the deformation behavior of materials. Elastic materials exhibit reversible deformation. When a load or stress is applied, the material deforms, but when the load is removed, the material returns to its original shape and size. Stress relaxation function. Stress relaxation is a key concept in rheology that describes how materials relieve stress under constant strain. When a material is subjected to a sudden deformation or strain and the stress is held constant, the material gradually relaxes or decreases in stress over time. This phenomenon is particularly important in viscoelastic materials, which exhibit both viscous and elastic properties. Creep compliance function. The creep compliance function is a key rheological property that describes the time-dependent deformation of a material under a constant applied stress. It is particularly important for viscoelastic materials, which exhibit both viscous and elastic behavior. Power law parameters is essential in rheology as they define how a material responds to shear stress and shear rate. These parameters play a crucial role in characterizing the flow behavior of non-Newtonian fluids, and are fundamental in predicting and analyzing the behavior of materials in various applications, such as fluid dynamics, polymer processing, and hydraulic systems. Applications of rheology. Rheology is a powerful tool in the food industry, providing valuable insights into the physical and functional properties of food materials, which are essential for product development, process optimization, quality control, and sensory evaluation. In soil mechanics, rheology is a powerful tool for characterizing the time-dependent deformation and flow behavior of soils, developing predictive models, designing tests, and analyzing new materials in geotechnical engineering applications. It provides a quantitative, physics-based approach to understanding soil mechanics. Rheology plays a significant role in geology technology by providing insights into the flow and deformation behavior of materials, predicting instabilities, understanding soil and rock mechanics, and analyzing the response of geological materials to stress and strain in various geotechnical and structural applications. The application of rheology in concrete technology enhances our understanding of concrete behavior, enabling the development of more efficient and effective concrete mix designs, placement, and finishing techniques. Rheology is a powerful tool in the plastics industry, enabling the characterization of polymers, prediction of processability, quality control, material development, and analysis of recycled materials. By providing insights into the flow behavior and molecular structure of polymers, rheology helps optimize processing conditions and ensure the production of high-quality plastic products. Tribology, the study of lubrication. Rheology and tribology are complementary disciplines that together provide a more complete understanding of the behavior of materials, especially in applications involving friction, wear, and lubrication. Next, what is stress and strain? Stress defined as force components acting on a body per unit cross-sectional area or area of the deformed specimen. While the strain is the change in size or shape of a body in response to the applied force. There are three stresses that are commonly applied to characterize foods mechanically. These are: compressive is directed toward the material, while tensile is directed away from the material, and shearing is directed tangentially to the material. Shear stress is the most prevalent with fluids or viscous materials. Since strain is the response of the material to stress, compressive shear and tensile strains can be found. When small deformations are exerted under compression, fluids can show a straight line in the stress-strain plot, and its slope is called the Young modulus of elasticity. Rheologically, a material can deform in three ways: elastic, plastic, or viscous. It can be denoted by a spring friction element and a dashpot arranged in series or parallel, respectively, in rheological models. There are some basic terminologies in rheology. These are: strain, the unit change, due to force, in the size or shape of a body referred to its original size or shape. Strain is non-dimensional quantity, but it is frequently expressed centimeter per centimeter, meter per meter, inches per inches. Under the strain is the linear or tensile or compressive strain. It is the change per unit length, due to force, in an original linear dimension. Axial strain is linear strain in a plane parallel to the longitudinal of the specimen. Transverse strain is a linear strain in a plane perpendicular to the axis of the specimen. Shear strain or angular strain is the tangent of the angular change, due to force, between two lines originally perpendicular to each other through a point in a body. Next is the stress. It is the intensity of a point in a body of the internal forces or components of force that act on a given plane through the point. Stress is expressed in force per unit area. Under the stress are normal stress, shear stress, and torsional stress. Normal stress is the stress component perpendicular to a plane on which the forces act. Under the normal stress there is two kinds of stresses. These are tensile and compressive stress. Tensile stress, it is the normal stress due to forces directed away from the plane on which they act. Compressive stress, it is the normal stress due to forces directed toward the plane on which they act. Shear stress, it is a stress component tangential to the plane on which the forces act. Torsional stress is a type of shear stress that occurs when an object is subjected to a twisting or torsional force. It is defined as the shear stress that acts on a transverse cross-section of an object due to the action of a twist. The classification of rheology is depicted in the figure. Under the deformation are elastic and inelastic. Hookean body and non-Hookean body is under the elastic deformation. Hooke's law is a principle of physics that states that the force needed to extend or compress a spring by some distance is proportional to that distance. Viscoelastic material and viscoplastic material. Viscoelasticity is the property of materials that exhibit both viscous and elastic characteristics when undergoing deformation. Viscous materials, like honey, resist shear flow and strain linearly with time when a stress is applied. Viscoelastic materials have elements of both of these properties and, as such, exhibit time-dependent strain. Viscoplastic materials are characterized by their time-dependent, irreversible deformation behavior under inelastic loading conditions, which is distinct from the recoverable deformation of elastic and viscoelastic materials. Under the flow are plastic and viscous. Non-Bingham plastic and Bingham plastic is under the plastic flow, while Newtonian and non-Newtonian flow are under viscous flow. Fluids are termed as Newtonian if the viscous stresses that arise from its flow, at every point, are proportional to the local strain rate, that is the rate of change of its deformation over time, like water. A non-Newtonian fluids are dependent on the shear rate or time, and the viscosity is termed as consistency or apparent viscosity. Under the non-Newtonian fluid are pseudoplastic and dilatant. The figure depicts the shear rate dependency. Bingham plastic, a minimum shear stress known as a yield stress must be exceeded before flow begins. Like tomato ketchup and mayonnaise. Pseudoplastic, in this type of flow an increasing shear force gives a more than proportional increase in shear rate, but the curve begins at origin. One of the examples is salad dressing. Dilatant, the shear stress-shear rate plot of this type of a flow begins at the origin but is characterized by equal increments in shear stress giving less than equal increment in the shear rate, such as raw starch suspensions and syrups. The figure illustrates the time-dependent behavior. Rheopectic, the apparent viscosity increases with time and the change is reversible, that is, the fluid will revert back to its original state on standing. Shear thickening, the apparent viscosity increases with time and the change is irreversible, that is, the fluid stays in thick state when the shear stress is removed. Thixotropy, the apparent viscosity decreases with time and the change is reversible, that is, the fluid will revert back to its original state on standing. Shear thinning, the apparent viscosity decreases with time and the change is irreversible, that is, the fluid stays in thinner state when the shear stress is removed.
So, to sum it all up, rheology is the study of flow and deformation of a material and is concerned with the question, how does a material respond to a force? Adios! See you in the next video.